Okay, in section 4.1 and 4.2, we're going to be looking at the probability distribution function for discrete random variables and the mean, which is also called the expected value, and standard deviation. So a random variable is a variable we denote it as capital X that has a value for each outcome of a procedure that is determined by chance. So for example, if we are flipping a coin, we're going to let X be the number of heads that we see in two flips. So what are all the possible values that X could be? Or basically, in two flips, how many heads could you see? Well, if I flip this thing 2 times, they could both be tails, which means there would be no heads. If I flip it 2 times, it could be 1 tail, 1 heads, or both of them could be heads. So all the possible values could be 0, 1, or 2. Another example is the time between arrivals of cars at a drive-thru. So we're going to let X be the time between arrivals. So what are all the possible values of X? Okay, well, you could have one car pull up and then right behind it you have another car. Or a car could pull up and then another car, maybe an hour, hour and a half, couple hours, a day, a week, a year. Never. Okay, so this could be X greater than 0. Okay, so a discrete random variable versus a continuous random variable. The same thing that we were talking about at the beginning between discrete and continuous. So discrete is going to be, and you can look down here as well, it's going to count the occurrence, something that is countable. Okay. Whereas continuous, we said the best thing for continuous is measurements, heights, weight, speed, value, length. We're also going to add duration of time. So if we go back to these two examples, so the first one with the number of flips, was this discrete or is it continuous? Well, I can count how many flips or how many heads in those two flips. So this would be discrete. Okay. Now, this one is talking about a time or a duration of time. Therefore, it is continuous. Okay. We're going to distinguish between discrete and continuous for A through C here. So the number of A's earned in a section of statistics with 15 students enrolled. Okay, well, I'm going to go ahead and show you all the possible values for X. So with 15 people, nobody could have made an A, or everybody could have made an A, and everybody in between. So this could start at 0, go from 1, 2, 3, 4, all the way up to 15. And since I'm able to count how many A's I have, this is discrete. Okay, the number of cars that travel through a McDonald's drive-thru in the next hour. Okay, well, there could be no cars. Could be 1, could be 2, could be 3, could be 4, could be 5, could be 6, could be 7. It could keep on going. I really don't know how many cars could go through in the next hour. But since I am able to count how many cars have gone through that drive-thru in the next hour, this is discrete. Notice here the number. The number, okay? Now C is the speed of the next car that passes a state trooper, okay? Well, let's list all the values that X could be. Could X be 0? Could the speed of the car be 0? Well, no, it couldn't be 0 because then it wouldn't be moving and therefore it wouldn't be passing the state trooper. But anything greater than 0, it would be passing the state trooper. Now, this is going to be continuous because this is a type of measurement. We're measuring the speed of the car. Call it a probability distribution. It's just a table that gives the probability for each value of your random variable. So say we were rolling a die. we're going to let the random variable x represent the number the die landed on. So x could be 1 through 6 on a 6-sided die. So what are the probabilities for each x value? And we're going to say that this die is a fair die. So all your probabilities here would be exactly the same. It'd be 1 over 6 in each of these cases. Now if I add all of these up, the probability for the summation of, actually, the summation of all these probabilities would add up to 1. Okay? Now, this right here, this is your probability distribution. Okay, it's just a table. There's your x values right here, and then there's the probability for each of those x values, and that's it. Now, a PDF, which in statistics is different from the PDF that you're used to, probability density function, and this is for a discrete random variable, something that we can count. Okay. Now we got 2 rules. I just did one of them. If we add all of the probabilities, they're going to equal to 1. But each individual probability that we look at is going to fall between 0 and 1. So that means if we looked at, say, just 1, this individual probability will fall between 0 and 1. This individual probability will fall between 0 and 1. And so for this one, so forth, and keep on going. Each individual probability for an x value, just one of them, will fall between 0 and 1. Those are the 2 rules that always apply. Okay, now this is a PDF. Notice that the horizontal axis is the values of your random variable x, and the vertical axis are your probabilities. So here's your random variable x for your horizontal, and then here's your probabilities for your probabilities of that random variable x. Okay, now if we were trying to find the mean from a probability distribution, what you could look at is the original definition for your mean, which would be you would add up all your x values and then divide by your total. Now remember, the shortcut is if you had any repeats, you could just multiply. So say we had this data set. So if I was going to find the mean of this, then I would do 2 plus 4 times 3, because I have 3 of them, plus 8 plus 9 times 3, because I have 3 of them, and then divide by how many numbers I have. I would have 1, 2, 3, 4, 5, 6, 7, 8. Okay, same thing here. We are taking the x value, which each one of these, the 2, the 4, 4, 4, 8, 9, 9, 9, that'd be an x value, times the frequency. Okay, here would be 3, here would be 3. This would be times 1, so I didn't write anything. Divide by the number of values in my data set. This would be 8. Okay, now if I move this summation to the front and then move this in under the frequencies, well then frequencies divided by n, that's really just probability. So we could use this formula right here to find the mean within a probability distribution. So like this right here, what is the mean of the distribution below? And this little bit right here is the probability distribution. It's got your x value along with the probability for each of those x values. Now all you have to do is, if you notice back here, this formula is take your x times the probability of that x for each and every one of them. Once you do that, then you're going to add them all up. So we're just going to multiply straight across and get a number for each one of these. First one I'll get 0.05. For the second one I'll get 0.30. Then I'll get 1.05, and then 1.20, and then 0.50, and 0.30. Once I have all that, I'm going to add all these together, and that will give me 3.4. Okay? And notice, if I add this column right here, probability of x, this is going to add to 1. Okay, so the mean for this probability distribution is 3.4. Remember, this is a Greek letter. It represents the population mean. We say mu, so that is mu, or your population mean, is equal to 3.4. So what this says is, say this is rolling a die because it's 1 through 6. It's a weighted die because all the probabilities are different from each other. If it was a fair die, all the probabilities would be the same. But since they're different, it's a weighted die. So this is saying that you will roll more 3s and 4s, but more 3s than 4s. Because notice this 3.4 is just a hair closer to 3 than it is 4. So your expected value, or your mean, or what you expect to happen, you're going to be most likely will get 3s and 4s. Roll 3s and 4s, but you will roll more 3s than 4s because a 3.4 is just a hair closer to 3 than it is 4. And then trying to find variance for your probability distribution. Now notice, if we look at this formula right here, just notice this little part right here. Okay. Remember, variance and standard deviation were very close to each other. When I go from variance to standard deviation, then what I would do is square root the number. If I was going from standard deviation to variance, then I would square the number. Okay, so keep in mind this, all these symbols here go from variance to standard deviation. Notice everything inside here exactly the same, except for now you've got a square root over it. Okay, so you can use either one of these formulas, either this one or this one for variance, and either this one or this one for standard deviation. Now if you look at this one right here, we'll be using this formula right here. So what we need to do is we need to square our x values. Once we do that, then we need to multiply times the probability of that x value. And we also need to find the mean of this probability distribution and square it. So first thing is we're going to square all of our x values. So we're going to take this column right here and square each number. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. Okay, and then what we're going to do is we're going to take x squared times the probability of x. So we're going to take this column and multiply it times this column here. What you would get is 0.05 for the first one, and then 0.60, and then 3.15, and then 4.80, and then 2.50, and then 1.80. Okay, so that was this little part right here. The one little thing, I need a summation symbol in front of that, because what we need to do is add all of these numbers together, which once you do that, you get 12.9. So that is just this first number right here. Now to get your variance, or not your variance, but your mean, you need to take this right here, your x values, times your probability of that x value, and add them all up, which is what we did in the last exercise, which we got 3.4. So this is going to be 12.9 minus 3.4, but don't forget to square it. So 12.9 minus 1156, which will give you 1.34. And then there's your variance for this distribution.